All right, so for example number 2 here, we are going to look at a couple different functions, and we're going to be mostly talking about the order, and we're going to see that order is important. So I've kind of talked about it before, but I'm going to really stress it in this example here. So in example number 2 here, we have a function f of x is equal to x minus 3, and g of x, which is equal to the square root of x. And here we need to determine both f of g of x and g of f of x. And if you guys want to, if you guys prefer this, we can rewrite f of g of x. We can rewrite that to look kind of like example number 1. So we can write that as f of g of x, if you guys want to. If not, that's absolutely fine. So what we're going to do is we're going to take g of x and we're going to substitute it into f of x. Here we're not given any values for x, so we're just going to take, we have g of x is equal to the square root of x. We're going to take square root of x and put this into f of x wherever we see x. So here we'll have f at the square root of x is equal to x minus 3. We'll substitute that value in. So the square root of x minus 3. Okay? For b here, now we're going to be dealing with g of f of x. And if you want to, we can rewrite that as g of f of x, like that. So we're going to take f of x, which is equal to x minus 3. We're going to substitute this value in for x in our outer function, which is g of x. So we have g of x minus 3. That is equal to the square root of x. And substituting that value in, we have the square root of x minus 3. Now, if you guys compare both f of g of x and g of f of x, are those the exact same values? And hopefully you guys can see this, but the answer here is no. So in f of x, or f of g of x, here are negative 3, or subtract 3, that is in the outside of the square root, whereas with g of f of x, it is inside that square root sign. So does order matter when composing functions? Yes, absolutely. Order does matter. These are not the same function. Alright. So even if we compare, so if I could say this out, f of g of x does not equal to g of f of x. Okay? So order matters. Now let's move on to example D here. And here we need to state the domain of each function. So that is f of x, g of x, f of g of x, and g of f of x. So this is going to be kind of going into what I talked about earlier, is that our domains are not necessarily the same as what we would have looked at before. So we're going to see in one of these examples that the domain has nothing to do with the previous domains. Okay? So here we had f of x. And if I could write that out, f of x was equal to x minus 3. It'll help me to see the domain here. You don't have to rewrite it, but just because it's at the top of my screen, I'll just rewrite it for purpose sake. All right, and so when we're talking about the domain of f of x, we have that x such that, and ask yourself, does it matter what x is? Will any value for x create a non-permissible value? And for that one, the answer is no, x can be anything. So we'll say that x is an element of all real numbers. Then looking at g of x, that one is equal to the square root of x. And then ask yourself, can x be any value? And for that one, this one is a no. What is special about the square root of x? If you guys remember that, there's certain values that x can't be. And x can't be negative numbers. It can be 0 or positive, but it can't be negative. So we can say that x must be greater than or equal to 0. That's important. It can be equal to 0, but it can't be less than. And then we'll finish off by saying that x can also be an element of all real numbers within that restriction. So then looking here at f of g of x, that one there was equal to the square root of x minus 3. And then you can ask yourself, for what value can x not be, or which values can it be? So we'll say that x such that, and here, this one here is a coincidence, but here it's actually the same restriction as g of x. So x must be greater than or equal to 0. So look at what is under that square root symbol there, and now there's just x. So x must be greater than or equal to 0, where x is an element of all real numbers. And lastly there, we're going to deal with g of f of x. That one there was equal to the square root of x minus 3. So our domain there, we have x such that. And what values of x can we not have? So this one here, this entire radicand, that's the variable or function within that square root, when will this equal to 0? So what you guys can do is, if you can't see this right away, but what you can do is set this equal to 0. So you have x minus 3 is equal to 0. Move 3 to the other side, so we have x is equal to positive 3. So that means that here our x can be equal to 3, and if you guys play around with those values, you can do a test point, but if you notice any value greater than 3 will give you a positive value, and any value less than 3 will give you negative value. So x must be greater than or equal to 3, where x is an element of all real numbers. So if I could point out with this domain, notice how it really doesn't have any overlap with the other 3 domains. So it's really important to find that composite function, then look at what the restrictions are, okay? So now let's move on to example number 3. So here we're going to be dealing with some sketching and some graphing. It's going to be wonderful. And so here we have a function f of x is equal to x squared plus 1. And we also have a function g of x is equal to 2x. Here we need to determine the equation of each composite function, graph it, and then state its domain and range. So in part A here we have y is equal to f of g of x. So to answer the first part of this question, we need to determine the composite function. So here we have g of x is equal to 2x. This here is our inner function. So we're going to substitute 2x for each x in f of x. So we'll have f at 2 of x is equal to, that'll be x squared plus 1. Substitute this in for x. That is equal to 2x squared plus 1. And just make sure this squared applies to this whole term here. So it's 2 squared times x squared. Okay? So then applying this squared, we have 4x squared plus 1. And that is our composite function. So y is equal to 4x squared plus 1. Then, now we need to graph it, and I'm going to do table values over here. And if you guys notice here, we have a squared term. This is a quadratic equation. So we're going to end up with a parabola. It's going to be wonderful. So to start, we can, if you guys can see the vertex right away. If not, let's just graph some values. Let's see if we can find it. So we can start off with our nice values. Maybe let's go with -2, -1, 0, 1, and 2. And then if we need to, we can either add some more values or do whatever we need to in order to see the shape of that function. So to put -2 in for x, we have 4 times -2 squared plus 1. That is equal to 4 times 4. So -2 squared is 4 times 4 is 16 plus 1. And that there is equal to 17. Substituting in -1 for x, we have 4 times -1 squared. If I could do -1 squared, that's just equal to 1. Plus 1. So that there is equal to 4 plus 1, which is equal to 5. Then substituting in 0, we get 0 squared times 4. So it'd be 0 times 4 is 0 plus 1. And that is equal to 1. Then substituting in 1 for x, we have 4 times 1 squared, which is just 1, plus 1. That there is equal to 4 times 1 is 4, plus 1 is 5. So here, if you guys can take a guess, our next value should be 17. We're dealing with a parabola here, so it should follow that same pattern. We can make that conclusion here that x is equal to 0 and y is equal to 1 is our vertex there. So following that pattern, we should get 17 for x is equal to 2, but we can double check it if you like, just so we can double check. So we get 4 times 2 squared, which is 4, plus 1. That is equal to 4 times 4, which is 16, plus 1. And that is in fact equal to 17. Awesome. So now we can start graphing. We have enough values, we see our vertex, we see where this parabola is going, so now we can graph. And here our biggest value here is 17. And if you guys like to, I know I think Miss Windrum talked about only needing 2 points plus a vertex. So if you want to, we could just graph from -1 to 1. That would give us a much closer up graph. But you also could do the -2 and 17 and 2 and 17. Both of them will be fine as long as they see a minimum of 3 points. If you want to do all 5, that is absolutely fine. I think that's what Miss Windrum did. If not, correct me. But I'll try and keep with how she was working with equations. So let's maybe just go ahead and we'll just graph these 3 points. We'll keep it nice and small. We see what's going on there. So we can label each, maybe every 4 tick marks will be, we really could go really big if we wanted to. Since we're not dealing with very big values, just 0 to 1. Although our y values will range from 5 all the way down to 1. So here we'll do every second tick mark will be 1 unit. And we'll just do a couple for the negative values. We don't need to go too in depth since we're never actually going below 0 there. Okay, so for our first one there we have x is equal to -1, that is equal to 5. Then we have x is equal to 0, that is equal to 1. And then x is equal to 1, and we're at y is equal to 5 there. Okay, so then we have at least 3 points. That should be good enough to see what on earth is going on with our graph. And so from here, let's just connect our dots. All right, and then let's label our function there. So here we have y is equal to 4x squared plus 1. And then we can talk about the domain and the range. And I'll just write this down here. So here our domain for our composite function there. So we have x such that, and if you guys notice, even just by examining, we have 4x squared plus 1. That one, it doesn't matter what value of x we have, so we can say that our domain is x is an element of all real numbers. It doesn't matter what x is. Then dealing with our range, that's looking at our y values. So we have y such that, and from what we know about our parabolas, we know that it will never, start to do a curve and end up turning around and going into negative direction. So we can say that our lowest point possible will be this vertex. So that is where y is equal to 1. So y must be greater than or equal to 1, where y is an element of all real numbers. Okay? So hopefully from there we should be good. We know how to graph. The only thing new is finding this composite function here. So we're getting close to our 50-minute mark, so we're going to switch over to video number 3 to finish off graphing b and then to determine one last function there. So probably be a fairly short video there. So if you guys want to, I encourage you try b and then number 4 yourself. But if not, we will see the solutions in the next video.